Fraser TV series. It's on South Korea. you want to re-enter your address, then you can click send.
Okay, I'm gonna make an announcement to pass out trivia sheets. I'm not gonna bother you. This is just trivia sheets. Will you help me? You're busy. I'll do it. Okay. No worries, I got this. I hope we have enough trivia sheets. It looks like we're organizing our own. Okay. This is very loud, isn't it? Hello. Hi everyone. Welcome to Astronomy on Tap. We're going to get started very shortly. But first, if you want to participate in trivia, please come see me at the front to get a trivia sheet and a golf pencil. Thank you.
Have you used one of these before? Okay, I'll just leave this here and you can put that on just before you go up. It's just a mic for the streaming.
So how do I turn it off?
Oh, there's a button on top here that'll turn it off, but I can get you from my end as well. If you hold this button down.
Oh, okay.
And it's on the light.
You have to turn it on again, right? Wonderful.
I have index cards. There are index cards that you can write your answers on. Answers, so are you sure? Okay, thank you. Then we have this right. I'm gonna ask. Totally understand. Hello. everyone. Hello again. Welcome to Astronomy on Tap again. It's good to see you all. We are about to get started with trivia like we normally do. There is a slight difference tonight between tonight and past Astronomy on Taps, and that is because Bruce Balick, who was our speaker in March, is back to give a full hour-length talk about cosmology, which absolutely deserves a round of applause. Thank you. He liked you guys so much that he wanted to come back. So, the format, however, of the event is going to stay the same. So what we're going to do is go through the trivia questions. Per usual, you'll have 30 seconds per question to get your answer down, and then I'll go back through all the questions, but this time you'll only have 15 seconds. We'll collect the trivia sheets, and Bruce will get started with his talk. He'll speak for about 30 minutes, and then we'll have an intermission, during which time we'll announce the trivia answers and winners, and then Bruce will finish off the event with the second half of his talk. That was a lot of information. Does that make sense? Good. Okay. So we're going to get started with trivia in that case, and it's random astronomy and space questions. So 30 seconds, a question. Don't forget. Very scatterbrained today.
You we're gonna flip through the questions one more time.
Oh, you're kidding? Okay.
And then we'll be good to go. Okay, so that was the first round through all the questions. Now I'm going to put them all up one more time and only show them for 15 seconds apiece this time. Can everybody see the slides? Okay, cool. Thank you. Okay, after this, can you collect the trivia sheets while I get the laptop switched? Or do you want to do the laptops and I'll do the trivia sheets? It doesn't matter.
Either way, I'll have to like refresh one thing on my side, but I can do that.
Okay. I can also, as soon as we kind of get them unplugged, I can jump over and help you and take over. We're low on staff, and by that I mean it's only me and David. And so, will you help us collect the trivia sheets? Sure. Okay. 5 more questions, 15 seconds apiece, and then I will tell everybody to bring where they can and I'll be switching. Thank you. Is your laptop ready to be switched?
I'm ready.
Cool. Just have one more question after this. Okay, hopefully everybody got their trivia answers down. At this time, could you please bring your trivia sheets and golf pencils up to Joseph in the front, please? Thank you. We're going to get the speaker set up. Okay. You ready? Great. Do you want to grab this up? Do you know how to switch presentation mode to it on a Mac? I don't know how to do it on a Mac. I don't know how to do it on a Mac, do you?
Use slideshow.
Yeah, I think the issue is it's not duplicating the screen. You know?
You know how to do it on Mac? You know how to do it? I work at school and do this all the time.
Oh, okay. Do you know how to do it on a Mac?
Am I live?
Let me see. You might have to hold down the button that's at the bottom. Oh yeah, you're good. It's on.
So that one's for the streaming. So the mic over there is the one that's.
Oh, we're in full. He's already in the presentation.
So this works, but it's for like people watching online.
I have to come over here and change slides, so I'd really like this to be live.
So that's live for people online, but the mic over there is the one, so you can take it off the
Display. Where's duplicate? Sees it. Why is it not letting us duplicate it? If he goes into presentation mode, because it sees both displays, well, it should have been showing his background. Get your attention for just a second. We're having some startup.
Sorry, you have to project a little with that mic. Oh, brilliant.
so it's I'm not able to capture it.
Put it in my mouth.
You got it. Yes, thank you.
So, as we get started,
I'm guessing we don't have a list.
there's one really important thing. Megan, who produces this evening?
Myself and the other graduate students.
The graduate students of the University of Washington. You couldn't. Megan,
And David live streams it. David.
Megan, what do you guys get out of it?
What?
What do you get out of it?
Experience to get experience public speaking, I guess, would be the thing we get out of it.
They're volunteers. They're doing this out of love.
And I might add that our undergraduates put on a public outreach program at the old observatory on the university campus 12 times a year during the spring and the summer. We're all sold out for this summer, but watch our website if you're interested in going. And unlike here, you can bring kids. Kids love it. The old observatory was built in 1895. The telescope inside it is even older than that. It's driven on a grandfather clock gear system, and you wind up cannonballs to make it go. It's an incredible thing to see. But tonight, last time I spoke here, it was dark out. And this is, you're kidding. But last time I spoke, it was dark out, and it was easy to see the slides. I think people in the back may have a little bit of a struggle. The problem here is the fact that the Earth is round and goes around the sun. So blame the astronomers. We did that. Cosmology is the study of the birth and the evolution of the universe and the structure of the universe. Actually, the word formally means the structure, but today we use it to mean structure and evolution. It's perhaps a question which has troubled humankind, for a long time, and every culture has a story of how the universe began. The story tonight is based on evidence, right? So that makes it scientific. But wait until you see how thin the evidence actually is. Right? That's it. I can't do it. At the end of the slide, I have a nice wrap up. It says, that quotes Mark Twain, who has a way of saying things like that very, very poetically. So there are many, many questions that people ask. Whoops. There. These are among the most common. Oh, I'm going to trip. It's dangerous up here. These are the most common questions that I've been asked in my almost 50 years of teaching at the University of Washington. Wonderful, wonderful career, wonderful students, and great research, and wonderful support from the university as well. These are questions you have all asked yourself, maybe when you were much younger, right? And maybe you didn't ask every question, and you'll be happy to know that not every question on this list has an answer, right? So we're wading into territory which may be a little bit strange. Keep drinking beer. Can I move this down here?
I can advance the slides for you if you'd like.
Oh, okay. So you're going to have to keep an open mind. Things are going to start out not terribly strange, but as we get into the first, this talk has two halves. The longer half is the one we're going to do now. It's in many ways the most difficult of all to follow. It's what we realize and have realized without any theory of the Big Bang. We realize this about the nature of the universe. It's based on some really very simple observations that have been around for the most part for a long, long time. Yes. All right, that's the cue to have a sip. Now, some of these questions are pretty simple and straightforward, and here is the simplest of all. How big is the universe? Anybody want to take a stab at that? The answer... So the universe is not infinitely old. The universe was born in what we call the Big Bang. We know that, right? We know that the universe is not infinitely old, not because of the theory, but because of the simple observations that Hubble made in 1929. The age of the universe can easily be measured by the expansion of the universe. The size of the universe, and by this I mean the knowable universe, is the distance that light can travel since the beginning of time. Right? So the universe is 13.8 billion years old. The size of the knowable universe, the visible universe, is obviously 13.8 billion light years. That is a gigantic number. But the universe is going to be around for much, much longer than that. The universe is basically in its youthful stage right now, possibly just entering adulthood. Now, one very important thing about the universe is it is absolutely monotonous. It is boring. Everywhere you look, it looks the same in every direction. This is a shot from the James Webb telescope. This is the deepest image into space that we have ever obtained. And we look in different directions, and pretty much you get, the galaxies are not in precisely the same location, but the statistical properties of the universe, the large-scale structure of the universe, is the same no matter where we look. And that allows us, Megan, to justify, do it again. the so-called cosmological principle. Right, the cosmological principle is a very important principle because it allows us to fill in many, many gaps in our knowledge. It's an assumption that we make. It's a very reasonable assumption. Next. Go back.
Oh, sorry.
Okay, we'll work with this. So the Webb image shows the monotony of space, and that allows us to assume that not only in the visible, knowable universe, but even beyond it, space is pretty much the same. There is no evidence to the contrary. And that means the universe is both homogeneous and isotropic. Isotropic means the same in every direction. Now, that doesn't mean that this is a static universe, that the universe we see around us is the same sort of universe of a long time ago or a long time in the future. The cosmological principle allows for evolution. It just says that as the universe evolves, it all evolves in the same way all the time, right? So we can look back into space, and we have many times. We see galaxies that are younger, all of them at great distances, than they are near us. And that shows that the universe is a universe of change. There are many other ways to show that. So these are the kinds of things these are tools, these are assumptions, really. We can't prove that they're right because we can't see beyond the edge of the visible universe. But in order to construct theories of how the universe evolved, we have to make some assumptions about the things we can't see. Next. Now, this is kind of interesting. How can we explore cosmic history? As we look out into space, we're seeing things that emitted their light to us. If they're nearby, they emitted the light very recently. Next. So we see sunlight, we see the sun, rather, as it was 8 minutes ago. We see the nearest star, Proxima Centauri, as it was 4¼ years ago. We see the Orion Nebula as it was 1,500 years ago. What is it now? It'll take 1,500 years for its light to reach us, and only then will we know for sure. The center of the Milky Way is 25,000 light years away. We can't see it because it's hidden, we can't see it visibly because it's hidden by dust, but we can see it in radio waves, and as you may have heard, a huge black hole, 4 million times the mass of the sun, lurks at the galactic center. The nearest galaxy that looks anything like us is 2 million light years away. So we can look at it and pretty much assume that that's the way that we look, our galaxy looked 2 million years ago. Now, the most distant galaxy that we've ever seen, I have to update the number there. The most distant galaxy that we've ever seen is somewhere in the ballpark of 13.5 or 6 billion years old. Right? We see it at the time that it was forming. These ancient galaxies, the ones at the limit of Webb's vision, are not like ours. They're very ragged. They're filled with hot stars. Otherwise, we wouldn't be able to see them. So the universe of change allows us to, and the finite speed of light allows us to look back into time and see how the universe evolved, to study cosmic history. And that's something that no faculty member in our history department can do. Now, as we do that, we look in what's called the local neighborhood. That's within roughly the first few million light years. And we see a very familiar universe.
Is it this one?
Okay, could you go back one?
Oh, sorry, I'm trying to keep up here.
So there's an astronomer on the right side looking way, way, way back out into space and seeing things further and further and younger, we could, in principle, we could see the Big Bang itself, except the universe doesn't cooperate. I'll say a little more about this later, but let me just mention that for the first 350,000 years of cosmic history, the universe was not transparent. We can't see through it. It's just as opaque as this wall over here. So we can look back, and we do look back to within about 350,000 years after the Big Bang. After that, all we see is the wall. Now, I'll mention this a little bit later, but that wall is not blank. There is structure on that wall that comes from the earlier evolution of the universe. So looking at that wall and the inhomogeneities that are on it allow us to infer how they got there. And that's one really critical way of exploring the earliest universe. Okay, next. So as we, a pointer, I should have brought one. As we look back, so we're in the middle of the knowable universe. Its edge is 13.8 billion years. Oh, thank you.
Yeah.
Can people listening remotely see this?
I think so. Oh, no, not on the live stream.
Okay, all right. I'll be cautious. But for the audience here, okay, Megan.
It's the green button.
Ah. So we're at the center. We look out. The universe is uniform in a statistical sense. It looks the same. As we look out, it keeps getting younger and younger and younger. That opaque wall is this yellow circle here. It's 350 light years thick. And the Big Bang lurks behind it. Next. All right, so one common question is what's outside the universe? We can say, I think, without any reservation, we will never know for sure because we can't possibly see it. Now, it's true that the size of the knowable universe is getting bigger at a rate of 1 light year per year. So every year we can see incrementally further than we saw the year before. But humanity is not going to be around for another few billion light years, another few billion years. And so there's very little hope of really capturing through observations what's on the other side of the edge of the visible universe. But probably more of the same. The cosmological principle allows us to infer that. I've covered this. Skip to the next slide. Thanks. Okay. Time for a little more beer. We're going to do a little homework exercise. It's a very simple one. I'm going to ask you to help me here. It's 1 slide long, and it's going to give you a flavor for what's coming up after the slide. What is the simplest possible universe? The simplest possible universe. The simplest universe is the one that takes the fewest decisions to design. So any suggestions for the let's say the size of the simplest possible universe? Say again.
She said a neutron. She said a neutron. A neutron.
A
Size?
neutron, that's too small. But I mean, you made a decision. I'm looking for a size for the universe that really is generic. Let's try infinite.
Infinite.
The size of the simplest universe would be infinite because that's the simplest thing we can imagine. We know the universe is big, But infinite, in this exercise, infinite, I think, is a very good answer for it. How old would it be? Infinitely old, exactly. What about motions of the universe as a whole? Our universe is expanding. Would the simplest universe be one that's expanding, contracting, static? Who votes for static?
Einstein.
I mean, this is an exercise, so nobody's right or wrong. What would you put in it? Nothing. Right. You're a great audience. When I do this in Astronomy 101, I have to coax all these answers out. You have beer, the students in the classroom don't. Next. Okay, now we're going to come back to reality and ask a couple of questions whose resolution is really profound, okay? So Chicken Little predicted that the sky would fall. What's stopping the sky from, it hasn't fallen, so what's going on? What are some ideas for explaining that?
Dark energy.
Sorry?
Dark energy.
You're way ahead of me. We're trying to keep this very, very simple. He said dark energy. Dark energy, it works really well, but so why haven't the stars fallen? Yes.
They're too far away.
Well, that's a darn good answer. Now, if the universe were infinitely old, that wouldn't matter, would it? It would have crunched by now. Right? So, one possible way of explaining this is just what you said, basically. It isn't old enough. There hasn't been time for the crunch to happen. Any other ideas?
The motion of it just keeps it going.
I'm sorry,
The motion of everything just keeps it going.
it's expanding.
Yeah.
That's exactly right. If it's expanding fast enough, it can't collapse. So if you take a stone and throw it into the air, it goes up, but eventually it turns around and comes back down again. There's something known as the escape speed, which on Earth is 11 miles per second. And if you can throw the stone up at that speed, it will never come back. The Earth's gravity will never stop it, right? And so expansion is another possibility. That is wonderful. There's another possibility. Maybe. Sorry?
He said it wraps around. The universe wraps around.
Oh, the universe wraps around. I don't see how that.
It's all orbiting. Centrifugal force keeps it like
There's an opposing force.
Centrifugal force.
Yeah.
Oh, okay. Yeah, that would work. There's no evidence for it. But I mean, we're looking for hypothetical possibilities. What I'm really looking for is that the universe has a finite age. It may be infinite. The stars in the back, way far away, have not had time. Sorry, that's why it's a nice sky, dark.
Oh, sorry.
I goofed on that one.
I'm trying to keep.
Okay, so now we'll talk about why isn't the night sky bright? If we lived in an infinite universe, that really simple universe, and if that universe is just sitting there, not expanding, right, then you would expect that every line of sight up into the sky would land on the surface of the star. And that the sky would be as bright as, if all stars were like the sun, the sky would be as bright as the surface of the sun. And you can show that mathematically. If the universe is static, and if it's infinite in size. So resolving this conundrum suggests it may be expanding, or it may be finite in size. That is, those stars between that lie in the areas of darkness just haven't had time for the light to arrive here yet. So, a finite universe would do it. An ageless universe, right, would do it. That is, a universe of infinite age would have stars out there, but their light just hasn't arrived yet. And finally, an expanding universe. This brings us to the concept of the Doppler shift. Could you, yeah, can you click on the, do we have sound here? We don't, do we?
I don't think so. Sorry, I was.
People at home do. Oh, okay. So I'm going to assume that you're vaguely familiar with the Doppler shift, but if you haven't, you may not be, and I'm going to go over it very quickly. Imagine that you're standing along a road, and a fire truck with its siren screaming comes at you, passes you, and then moves away. What happens to the pitch of the siren? The siren shifts to lower frequencies after the fire truck has passed. The train has the same effect, right? You hear the train coming at you, you hear it going away, the sound shifts from eh to ah. That's a lengthening of the waves. So when the train is on its way at you, the waves are compressed and the frequency seems to be higher as the waves pass you. As the train is receding, the waves are stretched by its motion and the pitch goes down. So the Doppler shift would be very important, could be very important in an expanding universe. And one way of resolving this conundrum is to say that the distant stars are there, but their light is Doppler shifted out of the visible part of the spectrum into something that we can't see. So these are three possibilities that emerge from these very simple observations. The sky hasn't fallen and the sky is dark at night. Newton recognized many of these possibilities back in around 1700. So these are not new ideas, but they're of profound importance in understanding cosmology. Okay, next. Now, Edwin Hubble, the name is familiar to all of you, in the 1920s, he and a small team of people using the new 100-inch telescope at Mount Wilson above Los Angeles were taking pictures of galaxies. At the time, it wasn't clear whether galaxies consisted of pools of trillions of stars or whether they might be nebulae like the Orion nebulae. And so Hubble set out to take their photographs. He suspected that they consisted of stars, but to find out for sure, his colleagues, Humison and Cypher, obtained spectra of the light from galaxies. Stars have a very different sort of spectrum from nebulae, and it became quite clear that these objects, called galaxies, were filled with stars. And once you know something about how bright a star is, you realize immediately that these galaxies are very far away. But there was a little surprise waiting in the spectra. When they compared we're going back to the Doppler shift. The light from stars contains a lot of features in its spectrum. If the object is moving away, those features are shifted towards the red side of the spectrum. And from that, you can tell how fast a galaxy is moving either towards you or away from you. Is that fairly clear? So what Hubble found was a pattern that he never expected to find. That is, that further galaxies have larger redshifts than nearby galaxies. And in fact, there was a very simple relationship between a galaxy's distance, which he could measure using the light from the stars, and their speed of recession from us. None were approaching, but there's only one that's approaching, the nearest one. Galaxies have some random motions, but all the others follow this very consistent pattern shown in this graph behind Hubble here. This is a graph that he published in 1929, and the trend is absolutely clear. His data weren't all that good. They're much better now, and the trend persists, but the scatter in the points has almost gone away. So the way to visualize, a simple way to visualize what he saw is to imagine that the universe is like the surface of a balloon. There are galaxies on the surface, and the balloon is expanding. When you think about it for a minute, galaxies on an expanding balloon follow the pattern that the further they are, the faster they're receding. So just think about that for a second. It should be fairly obvious. So, boy, we're having no, go back.
Oh, sorry.
The projector's taking all the life out of these colors here. So what you're supposed to be looking at is a loaf of raisin bread that's been put in the oven. Right? The bread is a matrix which holds the raisins. Our attention is on the raisins, and as the bread expands, the raisins move apart from one another. Right? And they too will follow this pattern of the further apart they are, the faster they recede from one another. That's another way to, and I think a much better way to visualize what Hubble found rather than a balloon. Next. So all these galaxies are moving away from us. Right? What's wrong with us?
They got to know us.
Now, I always give this as a homework problem in Astronomy 101. It turns out this pattern of motion is the same for every observer, no matter which galaxy they happen to be on. Move yourself to another galaxy, and in an expansion in which the speed increases with distance, will preserve the relationship between speed and distance, no matter where you are. Everyone will see the same thing. Right, so we're not at the center of the universe because everybody will see what we see and can make the same claim. Here are some of the spectra that obtained back in the old days, and it's a little hard to see with the light here. There are faint black features. This is the spectrum of a star, and there are atoms in the atmosphere of the star that absorb certain wavelengths of light. They tend to be blue, which is on the left here. And these are galaxies whose relative distances you can see from their size. The smaller ones are the furthest, and the little black lines have moved over here to the red side of the spectrum. So that's the evidence for the expanding universe. And here is Hubble's graph, and here, where you can't see it, it's a much more modern plot. Hubble's realm was this little square down here, and if you can see the images, the data points, they lie along a line that goes all the way to the top here. So this is a uniformly expanding universe. Next. Okay, this shows a plot that you can see. These are supernovae whose distances can be measured from their brightness. Supernovae are exploding stars, and a certain subclass of them all have exactly the same luminosity, just as car headlights tend to have about the same luminosity. So the fainter they are, the more distant they are. And this shows the trend that we see out to 2 billion light years, 2 billion, which isn't very far. I mean, the universe is 13.8 billion, the knowable universe is 13.8 billion years. So this is a graph made back in the early days. And the speed of recession here goes up to 40,000 kilometers per second. So kilometers and miles differ by a factor of 2/3. For our purposes, forget about the difference. The point is the trend is very clear. It's very, very clear. And there's no way to refute the expansion of the universe. Now, one nice thing about this Hubble law is that you can take the movie of the expansion and you can turn around and play it backwards. And you can measure the age of the universe from the time when all the galaxies crunch together at the center. That would represent the Big Bang. So the age of the universe can be determined by these observations of Hubble and more modern observations to an amazing degree of accuracy. Right, okay. And I think this is where we take our break. What's the next slide? Yeah, okay. So this is where we'll pick up after you've had a little more beer.
We'll take a brief intermission so you guys can go refill your drinks, etc. And then when we come back, I will announce the trivia winners and the answers to the trivia questions. Thank you.
Good job. I'm wondering if we can get the clicker set up by any chance for this. I don't know that my computer will play nice with PowerPoint, but we can try. Is there any way that you can send me the PowerPoint file in Google Drive? Because if I can get it up on my computer. I do.
USPC.
I do not. Do you have a USB to USB of any kind? Is that going to mess everything up? Can you unplug it? that helps us usually. Long enough? Okay.
Okay, welcome back, everyone. Hello, welcome back. Did you all get your next drink? Nobody brought me a drink. I'm just kidding. Please don't. So, I have some good news, which is that I fixed the clicker with the help of David and Bruce in the intermission, so I will no longer have to advance the slides, and hopefully it will match better with the talk as we continue. But before I turn it back over to Bruce, I'm going to go through the trivia answers and the trivia winners. And on the trivia slide that's currently up on your screen, we also have a fun featured photo that was just sent to me by the principal of Bush School. So this image of M31, I believe is what it is. M21? 101. Oh, sorry, M101 was taken by the Bush School students, so we can all give them a round of applause. Yeah, oh, and there's a supernova in it that I didn't know. Here? Oh, okay. They caught the supernova as well. That's really cool. Great. They took it in Madison Valley. They did a really good job. You have a bunch of young budding astronomers. Okay. So,
I'm going to go through the trivia answers now, starting with number 1. Who was the first woman in space? The answer is B. I don't want to mess up her last name. Which astronaut wrote his daughter's initials on the moon? That would be Eugene Cernan. All right. Pluto is not bigger than the United States, believe it or not. Now we know why it's not a planet anymore, right? Okay. The first ever meal eaten in space was pureed meat and chocolate sauce. Ugh. Galileo is not credited with the discovery of Neptune because he thought it was a star. Proxima Centauri is the nearest star to the Earth other than the Sun. Now, this question we are going to note for a second. What is the most common type of star found in the Milky Way? As it turns out, red dwarfs are a subcategory of main sequence stars. So we kind of just made a goof there. But if you answered main sequence stars or red dwarfs, we marked you as correct because red dwarfs are the most common type of main sequence star. Hey, David, can you touch my laptop so it doesn't go to sleep, please? Thank you. Okay. You have to fly for 1,000 hours before you can apply to become an astronaut. Snoopy served as NASA's safety mascot. That makes sense because I think out of all of these people, he's the only one with significant flying experience, probably above 1,000 hours, right? Okay, and Alan Shepard flew in the Mercury, Gemini, and Apollo programs. So, we have 3 winners tonight. One of the winners got 9 out of 10 right and is slightly better than the other 2 winners who got 8 out of 10 right each. However, they didn't put their name on it, so they don't win, actually. I'm just kidding. I'm just kidding. Since you know who you are, you can win, so you guys can come up. So the first 8 out of 10 winner is Singularity. Well done. And the second 8 out of 10 winner is Kids Again. Well done. Okay. So if you won trivia, please come up at the end of the talk to get your prize before you leave Bickerson's. Did you want to say something in intermission?
Yeah. Hello, I'm Frank. I'm the owner with my wife up there, so just thank you all for coming out tonight. Yes, I'll take all the applause. She doesn't need to know you have the applause for me. So thank you all for coming out. Check our events. We have a bunch of talks this month, well, I guess next month because it's tomorrow, as well as Astronomy Back on Tap. And so we are now partnering. You'll see next time there'll be QR codes on the tables. We will actually have food that will be delivered for free starting next month. It actually should be here. We tried to get it all set up for tonight, but they needed a few more days. So it's going to be Cycle Dogs. That's right down the street here that used to kind of partner in this space. They're going to come up, set up table numbers and QR codes, so when Mean Sandwich is closed, you're still going to be able to get food. So that'll be something to look forward to for next month. So thank you again for all coming tonight.
Okay, so I guess that concludes trivia. Just give us 20 seconds to switch the slides, and Bruce will be back. Okay, so you will have this now. Let me just switch the slides over. Okay. Oh, you went forward a bit. Okay. Okay, good.
All right. Time for another swizzle of beer. All of the observations that we went through before, and a lot of newer ones, are all accommodated very nicely in the theory known to you as the Big Bang Theory. It is an incredibly complicated theory. We're certainly not going to go through the principles of how it was derived. But I can summarize the history. When Einstein in 1917 or 19, I can't remember now, when he published his general theory of relativity, he looked at an equation which is similar to one that Newton had, but with one important difference. And that is, the theory, in the general theory of relativity, there is no such thing as a stable universe. And long story short, if a universe is expanding, it can continue to expand. If it's contracting, it will continue to contract. The one thing it cannot do is just sit there. The forces of gravity will send it into a contraction. So, I mean, that was clear from Newton's day, but Newton had no idea about the expansion of the universe at the time. So the Big Bang Theory can be summarized in this cartoon. Out of nothing comes something. That was a conundrum back to the ancient Greeks. Their philosophers spent years asking the question, can you get something from nothing? And in the Big Bang Theory, you do. Well, you get something, us, from something that we don't understand and can't describe, something that has no laws of physics that we know of associated with it. So in the Big Bang Theory, the universe just materializes instantaneously. And the weird thing is, it was infinite in size at the time it was born. So out of nothing comes an infinite universe. Have another swig of beer. Whoops, wrong button. Now, the Big Bang occurs. When it occurs, our universe is born. It is born with all the matter that is now in it, all the energy that is now in it, right? Excuse me. And it's born in an incredibly dense and hot state. It's not stable. The energy, the thermal energy of the universe forces it into a rapid state of expansion, right? And I'm leaving out a lot of details here, very strange details, like the era of inflation, which if there's time, I'll come back to later. So this hot universe begins to expand. It was infinite at the beginning, it remains infinite, but things move apart in this expanding universe in much the same form that we see them today, but at slightly different speeds. The state of the universe at first was so hot, and if you're familiar with powers of 10 notation, the universe is born at a temperature of 10 to the 41st degrees Kelvin. And nothing, no state of matter is stable at that temperature except for the most elementary particles, which we can only speculate about. They're much more elementary than quarks. Who knows what they were? We don't. We don't have a theory for that. Now, as the universe expands, it begins to cool. And so there's a period of called inflation, which is necessary to explain the fact that the universe looks uniform. There must have been an event early in the universe that made the universe homogeneous, right? And I can go into more details about that later. The universe expands for about 350, 380,000 years in an opaque state. It is still hot, but it's cooling rapidly. It is hot enough that particles break apart into basic elementary particles, at least for a while. But then as the universe cools, the particles can still break apart, but they can't reform. So at first, you have matter and antimatter. Matter is making matter, light is making matter and antimatter. The energy of light is going into particles of both types. But those particles of both types annihilate one another and go back into light. As the universe cools, right, the formation process, which takes an enormous amount of heat, stops because the universe is too cold. The annihilation process continues on. Now, in a perfectly balanced universe, the matter and antimatter would be exactly equal, and we wouldn't be here. One of the big challenges of modern physics is to figure out why there was slightly more matter than antimatter. In the calculations, it looks like there was one matter particle that survived for every billion particles that had been around earlier. So we are just almost an afterthought in this annihilation process. But here we are, and we're here to talk about it, and we need to explain it, and there has been some progress on this that I don't understand. It's very deeply in physics that's far above my head. Anyway, at 380,000 years, the universe becomes opaque, and we can begin to see things that had been formed earlier, but now they can send signals to one another. We can see them, they can see us. And that brings us to the present era. Lovely cat walking around in front of me. So at the end of after 380,000 years, the universe became transparent, and that meant that blobs of hot material could radiate away their heat and form into smaller clumps of stuff, which continue to fragment and cascade until we make stars and planets. That's how we get here. We'll talk a little bit later about what's in the future, but it's the stars and the planets will be around for a long time. You can't make them go away. But the universe in which they are found is going to turn out to be a very, very cold, desolate place. So I'll come back to that. What triggered the Big Bang? We have no idea. To figure that out, you have to know the physics at the time before the Big Bang took place, and we don't know it. Now, we can conjecture that universes were being made out of whatever this stuff was that universes were made out of, not just our universe, but zillions of others. That's the concept of the multiverse, and that this universe creation process continues now and has been underway for basically forever. We don't know any of that. We don't know any of it, and there's no way to find out. But one way or the other, here we are, survivors. We can't look back before the beginning of time, right? Because there was nothing there to send light to us. So we'll never know for sure, but a lot of science fiction and a lot of really, really complex physics is being used now to try to explore this. And it's fun to think about, but as yet, they're just ideas, nothing that reaches the level of fact, verifiable fact. There are red characters up there which aren't very red and you can't see them. In the year 2000, there was just an amazingly difficult experiment performed. An experiment to measure distances in the depths of the cosmos. We had learned by then that supernovae, like the one you saw during intermission, were very useful for estimating distances. So any galaxy that had a supernova of the right type in it, if we observed the supernova, we could figure out how far away it was. At the same time, observing a supernova requires that you take a spectrum in order to figure out that it's a supernova. So we began to amass data on the nature of the spectra, in particular the Doppler shifts of these very distant supernovae as a function of their distance. What we found, and this puzzled people for a long time, and I think we finally have come to accept the fact that the Hubble law isn't really a constant law. That is, the universe is accelerating. The expansion of the universe is getting faster and faster, right? At a rate which is really astounding. It's hard to put that into words. You have to look at the numbers. But the acceleration of the universe is something we never expected to find. It was never predicted. It was found experimentally. And so we're in the usual awkward place of having to understand something without adequate physics to do it well. We use the term dark energy as a way to pretend that we have a way of explaining the acceleration of the universe. Dark energy, it's really, it's like Big Bang. It's a clever way of using two words to hide our ignorance. Right? I mean, dark and energy make perfectly good sense. Dark energy doesn't make much sense. It is, I have to emphasize, it is not predicted. You can go into the theory of general relativity and you can just stick a term in there, completely ad hoc, with no justification. And then you can fit the rate of expansion that we observe. But doing this is not physics, right? This is metaphysics. So dark energy is amazing stuff. There's a lot of it. There's a big universe out there with a whole lot of mass in it. And overwhelming the force of gravity to make a universe expand or accelerate takes an enormous amount of energy of some sort. What we do know is that dark energy is 3/4 of all the energy in the universe today. And most of the rest of the energy in the universe is in the form of matter, right? But the energy budget of the universe is being overwhelmed by the strange dark energy. So you know that we don't understand what dark matter is. We can characterize it. We can locate it. We can observe it. We can observe its effects on things that do emit light. And so dark matter, it's a state of matter that we don't understand, but we know where it is, and we know how much of it there is. Dark energy is even stranger. We know how much of it there is. It seems to be everywhere. if you go to Einstein's equation and put that term in it, then what you find is that dark energy is completely unlike anti-gravity. So gravity and anti-gravity, you can kind of imagine how they work with one another. The problem with dark energy is that the force that it exerts on particles or on anything increases with distance. Newton's law tells you that gravity gets weaker as things move apart, but this dark energy has increases in its impact on expanding the universe as the universe gets bigger and bigger. So it's a runaway situation. You can't see that. It's a cartoon from the New Yorker, which I really like. It's a way of portraying the acceleration of the universe. It's a way of saying that things in the universe are not only moving apart from one another, but moving apart at speeds which will increase over time. Now, what this means is pretty strange, right? So take two galaxies that are far apart today. They're moving apart from one another. Over the course of time, they'll separate at a speed which exceeds the speed of light. What? It turns out space can expand faster than the speed of light. It's just matter can't move through space faster than the speed of light. But space doesn't have that limitation. And so these galaxies spread through this rapidly expanding space will move apart until and their relative velocities will exceed the speed of light. And at that point, they'll be invisible to one another. They'll just disappear. So as this acceleration takes firmer and firmer control of the motions of the universe, things in the universe are going to move apart and become invisible to one another. It won't, I'm going to use the term, it won't be that long. We're talking hundreds of billions of years. But this radiation from that wall that we now see, that wall with the little bumps on it, and from which we learn about the earlier history of the universe, or infer the earlier history of the universe, that wall is going to disappear. And more galaxies are going to move apart faster than the speed of light, and they're going to disappear. And so I remember as a kid reading an Asimov science fiction story about stars blinking off one after the other. If you're my age, you might have read that. And that's what's going to happen. The galaxies that we see in the Webb images are going to disappear from our sight. We're going to be in a very, very dark universe. And of course, as the universe expands, it gets colder, just as any material gets colder when it expands. The universe today is at a temperature of 2.7 degrees above absolute zero, which seems awfully darn cold. It really is. It's very difficult in the lab to get, to cool things to temperatures that small. But the universe is going to get colder as it expands and get darker at the same time. It's a very dreary picture of our future. I lost. Oh, something. Okay, hang on. So, the big freeze and the big desolation lie ahead of us, not on a time scale that any of us have to worry about. Don't go out and sell your stock quite yet. So this is the wrap-up slide. You've seen what we've derived, what kind of information we've derived from just observing that the sky is dark and the sky hasn't fallen, that the universe is expanding, and that the expansion is accelerating. I love this quote of Mark Twain. Hello? Sorry. It's not coming up. Oh, there it is.
This is an excerpt from a couple of paragraphs that Mark Twain wrote in his book called Life on the Mississippi. I think it's very, very fitting. I love the context from which this is derived. And I'll show you, but you won't be able to read it because there are too many words. I keep hitting the wrong button, sorry. So there are all the words, and I'm going to leave them there. Basically, what Mark Twain wrote was he lived on the Mississippi River. The Mississippi River runs through what's basically a plain. And it's very difficult for the river to decide where to go because there just aren't hills to guide it. So the Mississippi River is filled with kinks. And after major floods, one of those kinks can be cut off or more. And Mark Twain wrote this. He says, in the space of, sorry, folks. There we go. In the space of 176 years, the lower Mississippi has shortened itself by 242 miles. This is an observation. These kinks keep getting cut off, and the river gets shorter and shorter. That's 1.33 miles per year. Anybody who's not an idiot can derive that 742 years from now, the lower Mississippi will only be 1.75 miles long. And that's where this quote about something marvelous about science comes from. With that, we end. Questions are fine.
Questions? Do you want to take questions?
Yeah. Well, it's rather late. Anyone who would like to leave, please do so without any fear of embarrassment. Anyone who would like to stay, I'd love to answer questions, if I can.
Yeah.
So we used to believe that the moon, the sun, the stars all travel around the Earth. So is it kind of presumptuous of us to think that the universe is expanding at an accelerating rate? Why don't we think we're shrinking at an accelerating rate?
Okay, folks, I wear hearing aids, and I had trouble, but Megan is going to tell me what the question is.
He said, back in the day, we thought that the sun and the moon and everything orbited around the Earth, and so accelerated rate. Why isn't it shrinking at accelerated rate? Why aren't we shrinking?
Why aren't we shrinking?
Yeah.
How do we know we're not shrinking?
Do you know why you're not shrinking? Do you know why you're not a black hole? Right? You have mass, you have gravity. You could, in principle, squash to a black hole. Why haven't you? The answer is calcium, your bones.
Question? Yeah.
Yeah. So that wall that you're talking about, from the previous astronomy minutes now, we kind of talked how it's the entire sky.
Yeah.
I wasn't able to ask this question then, but
Do you want to speak into the microphone?
In the middle, essentially. Yeah.
Here.
So,
Oh,
I'll walk in.
not long enough. Speak to the microphone.
Okay, cool. Here's my question. So that wall that Bruce was talking about, I think is everywhere in the night sky, right? It's like all around, which kind of seems like we're in the middle then, right? Essentially. So how are we not in the middle of the universe if we could see the wall in all directions, if that makes sense?
The only way that the answer will make sense is for you to finish your beer. In principle, everyone in the universe sees the same expansion from every possible viewpoint. The universe we see is in large scale the universe that they see. They see a wall
It's slightly different than the wall we see, but it's there and has little bumps on it left over from the history of the universe. So, yes, we're at the center of the visible universe that we can see. They're at the center of the visible universe that they can see. These universes are slightly different. The statistical properties, according to the cosmological principle, the statistical properties are exactly the same. Does that answer your question?
Yeah, it does. Yeah.
Hagen?
Yeah.
We have constants like the force of gravity, strong nuclear force, and all those. We assume those to be constant through the history of the universe. But if they aren't, it's because we already have the expansion of the universe we know is changing. So if those have those constants, what if they change? How would our universe be different? So I think my interpretation of your question is there are certain constants embedded deeply in the theory of gravity. The gravitational constant is the best known of these. The gravitational constant is critical in an equation that tells you how fast a rock that you drop will fall towards the Earth. It's the constant of proportionality between speed, between force and acceleration. Okay. And the question is, what if that has changed over time? If we assume that it hasn't, and any changes in it would have profound effects on the theory of gravitation, very profound effects. Off the top of my head, I can't say exactly where they are, what they would be. But that equation in general relativity that looks a lot like the Newtonian force for gravity, the expression for gravity, is basically an equation that equates the speed of motion, or the acceleration due to the force of gravity, to the mass that's there. And that gravitational constant, the one that you learned in high school, is embedded in the Einstein theory as well. So if that changes, I think all bets are off. The universe could accelerate, it could decelerate. It's fun to imagine what might happen. But we have looked for changes in the gravitational constant by measuring gravitational forces over the course of time, by looking way, way, way out into space, where in a younger universe, and we see no change yet.
One more question? Go ahead.
That was a great question.
So I just had a quick question about kind of two seems like contradictory ideas. One is about like relative speed. You're saying that there's nothing that has mass can travel faster than the speed of light. Yet space is not limited by the space can expand faster than the speed of light. So I guess what I was wondering is, it seems like we measure speed as relative to something else, say relative to us, for example. So how can it be that something that is massive, say like a star at the end of the universe, can then travel relative to us faster than the speed of light, even if things that are massive cannot travel faster than the speed of light?
Great question. It's difficult to answer it in a way that makes a whole lot of sense. Right? So, I don't know what to say. The raisins in the raisin cake can't move through the raisin cake any faster than some speed. Right? But the cake can expand faster than that. Right? If the cake is the entire universe and it follows the Hubble law of expansion, if you wait long enough, there will always be particles moving away from one another faster than the speed of light, being swept by the expansion of space. Right? Gravity has nothing to do with this. These things weren't fired off anywhere. They're just markers in this space which have always been there. And they just do what they slavishly do, what the universe, what space around them does.
Let's give another round of applause for the speaker.
That was great. And great job giving an hour-long talk. Not a lot of people do that here at AOT, of course. So thank you again. I'm going to give another round of applause. And great audience, yeah. So I just want to make the quick announcement that the next Astro on Tap will be here on June 28th. So that is the last Wednesday of June. I have not found speakers yet, but I will post those on the social media once we have speakers. If you want the trivia, come collect your prize. It is a sheet of stickers. Other than that, everybody get home safe, and thank you so much for coming.